Suppose a ball is thrown up into the air, straight upwards. So it's going to go up and then it's going to come down, right? I'm not throwing this in an arc. Just throwing it straight up and then down. And let's suppose the height is a function of time, is that function that you see right there. You get these kind of problems in calculus and even pre-calculus sometimes. When will the ball hit the ground? When will the ball reach its maximum height? And how high will the ball go? So, okay, and I did something kind of bad here. I forgot to include units. They are the kind of implied units here. Because of that negative 4.9, which is half of 9.8, you know, if you've had a little physics, that 9.8 meters per second squared is the acceleration due to gravity near the surface of the Earth. By the way, it's not true if you're up on the top of a mountain. Or maybe you say it's less true, it's less accurate. When you go further up into the higher elevations or into the sky, maybe in a spy balloon, the acceleration due to gravity is actually lower. Might be 9.7 meters per second squared or 9.6 meters per second squared. And if you're in the outer space, it's probably like 7 meters per second squared or something. Wait a minute. Why don't satellites follow the ground then? Why do they keep going around? Aren't they weightless? Don't they keep going around and around the Earth? They actually do eventually follow the ground unless you keep boosting them upward. What's keeping them typically from falling to the ground is because they're also going round and around really fast. So that's keeping them in orbit. There, you might say they're even continuously falling to the ground, but the Earth is round, and so they never hit the ground. That's actually how Newton imagined it. Anyway, where was I going with that? Just a little information. You did see there, like 7, 8 years ago, there was somebody who skydived from space, right? Did you ever see that? Went up in a balloon or something, got up to, I don't know, 50 miles high and skydove, and he fell straight to the ground, okay, because he wasn't orbiting. What was it, a 50? I forgot. 20 T plus, what was it, 1.5 or something? Plus 1.5. Okay, the implied units, because of the 4.9, are meters for distance and seconds for time. T equals time in seconds. H equals height in meters. It's actually a little easier to use if you use feet in seconds, because this becomes a negative 16 in that case. It's just a nicer number. When does it hit the ground? Set the height equal to 0 and solve for t, right? When does it hit the ground? Set h equal to 0, i.e. f of t equal to 0, and solve for t, equation solving. And it's quadratic. We can use the quadratic formula. Negative 4.9 t squared plus 20t plus net 1.5. Now, with such numbers, we should not expect nice roots, right? They're probably going to be irrational roots. So we'll be fine approximating them. Actually, one's going to be negative and one's positive. We're after the positive root. The graph of this function will look like this. We're after that root right there. That's the answer for when it hits the ground. Again, this is not the path of the ball. I mean, if you throw a ball horizontally as well as vertically, the path will look like a parabola. At least for a ball, not for a feather. All right, balls are not as affected by air resistance, and we are ignoring air resistance in this model. So we're after the positive root. Using the quadratic formula, we'll get negative 20, plus or minus in general, but well, careful. We'll actually use the minus one here because the A is negative. Wait a minute. Okay. That is going to give a positive number there. No, I guess we still will use the plus one. That makes sense? Yeah, I guess we still will use the plus one. So the ratio of these two parts is going to be positive because the negative signs are going to cancel out. But we do want the bigger root, so we will still use the plus. D squared is 20 squared is 400 minus 4 times negative 4.9 times 1.5. The most common place to make a mistake is maybe to forget that negative sign there. So negative 20 plus, okay, use my calculator. 4 times 4.9 is this times 1.5. And that is ultimately being added to 400. So we get 429.4 under the square root. And in all likelihood, that's not a nice number. Oh, no, it will be, excuse me, it will be the minus one. Sorry. I'm forgetting the minus sign has to go with the other one too. When you simplify it, we can cancel all the minus signs here. They will cancel. You can factor a negative one on the top and cancel with the minus sign on the bottom. So we get 20 plus square root of 429.4. 2 times 4.9 is 9.8. So we got to take the square root of this, add 20, divide by 9.8. That's approximately 4.1553, say, seconds. That's probably too many significant digits. You know, I'm not thinking about what's the appropriate number of significant digits here. 4.2 seconds. I mean, as far as how well the model does, you'd have to measure it against reality. For a ball of rock, it might be pretty accurate. For a feather, it's certainly not. For a feather, the original formula is not even a good model. We can double check it, maybe also by graphing the function. The function was negative 4.9 t squared, which has to go in as x squared in the calculator, plus 20t plus 1.5. By the way, the 20 does represent the initial upward velocity, 20 meters per second. And the 1.5 does represent the initial height, because when you plug in t equals 0, you get 1.5. There it is. Looks like it might be right. Let's confirm by calculating the intersection, or the 0, we could call it. Instead of looking for where it intersects another curve, we're looking for where it intersects the axis. Left bound, right bound, guess. 4.1553, yep. It's good. Okay, so basic physics application. We also want to figure out when the ball reaches its maximum height and how high does it go. Should have done this in calculus. How do you figure out when it reaches its maximum height? Yeah, when the derivative is 0, there's the time of the max height, because you want the slope of the tangent to be 0. You want the ball to be at the peak, meaning for an instant it's not moving. Wait a minute, does that make sense? How could it literally stop for an instant? Is that even possible? Don't worry about it. The velocity is dh dt is f prime of t is negative 9.8 t plus 20. To figure out the time when it reaches the maximum height, set this equal to 0 and solve for t. It's a nice linear equation. You'll get t is 20 over 9.8, which is a rational number. And as a decimal approximation, we get about 2.0408 seconds, say. That's the time of the maximum height. The max height itself is found by plugging that number into the function f of 2.0408. So square this number, multiply by negative 4.9. Add 20 times that number. Using more decimal places, and add 1.5. I'm plugged into the function. I get about 21.91 meters as the approximation for the maximum height. There's the graph again. Confirm it by going to the maximum feature here. Left bound, I guess you could just type in a 2. Right bound, say 2.1. Guess 2.05. Yeah, 2.0408 and 21.91. Okay, and double check things.